Okay, so thanks for inviting me for this web seminar. It's my first web seminar, so I hope the connection took 15 minutes, so I hope we can go ahead. The idea of my talk would be to show you how we can build covalent organic frameworks with atomic precision if we are able to guide reactions on surfaces, okay? And I see now that you were going through the paper, so maybe there are some slides that would be, well, not necessarily basic, but I hope that they are useful.
That's just perfect.
Okay, so you can think on these materials as covalent organic frameworks, but you can also think as a kind of graphene, nanostructure graphene, as a graphene sheet, as if somebody just took some atoms out of this graphene, but with atomic precision. And you know that this cannot be done. So that's why we have to go to tools or methods such as on-surface synthesis. So the idea for us to build this kind of materials, of course, is to build new materials with new properties, but it's also to bring additional properties, to imprint properties to existing materials. And that's what we wanted to do with this. That's why we build in graphene-based material, because we have to keep what graphene has, or most of the things that it has, and add more properties. Graphene is very nice, but it's still missing a lot of properties, such as these ones, right? It has no bandgap, it has no magnetism, if you don't do anything, or spinel coupling, superconductivity, it has no permeability. So if you're able to manipulate nanostructure, you can add some of them. We will talk about how to add a bandgap to graphene today. Also permeability, although we still didn't demonstrate it. So, I mean, if you want to add a bandgap to graphene or to induce a bandgap, the most evident, maybe a flexible way is just to reduce the lateral size to the nanoscale. And that's what we do, nanostructure. You can do that by using top-down approaches. Okay, you can go to the nanofabrication lab and you can punch holes to a graphene sheet so that you leave nano-size constrictions, and their electrons would quantize and you would induce a gap, effectively. By doing that, you will increase the on-off ratio of a transistor if you are able to make a transistor out of a graphene, because you know that graphene is a semi-metal, so you cannot really switch it off. If you induce a gap, you would be able to switch it off, but if the gap is small enough, you're still at room temperature, you're still having some current. And that's what happens if you build if you nanostructure graphene with top-down techniques. And that's because of the limiting scale where you can apply these techniques, okay? You can go to 10 nanometers or so, 7 nanometers or so, and the gaps that you can imprint are in the order of milli-electron volts. So in order to face the challenge of going to smaller scales, you can use the bottom-up techniques, and that's what we will be talking about today. And for instance, there are groups that they have shown that you can build also transistors with the nanostructures that can be built with the bottom-up techniques. You can go to very small scales if you use these techniques, even to 1 nanometer scale. And you can do that with atomic precision. You will see that how. So that means that you can induce gaps that are in the right order. They are in the 1 electron volt, same as silicons, for example. So you can, with this, improve the on-off ratios to reasonable ratios. This is the highest ratio that was achieved was 10 to the 5 with the graphene nanostructure. But the point is that, the limiting factors of the bottom-up techniques are that the size of these nanostructures, and also to control the distribution of the nanostructure that you build on the surface. So building nano devices out of that is still a challenge. We'll see how to improve this size and this distribution on the surface, but you will see that this is still a limit. Okay. So if you're able to have this graphene sheet with holes, you can also think on other applications. For instance, just to use a membrane, a graphene membrane for permeation Okay, you can filter water out of that. You can selectively filter gases out of that. You can even read DNA. You can sequence DNA because you can see how, as the DNA strand goes through a graphene membrane, you can see how the electric current that goes across the graphene can be perturbed in a different way, depending on the different amino acids. So this has been demonstrated, all this. The point is that, I mean, and using a 2D material for that is very effective also, because you can, you imagine that you only need to go through one atom. So it takes very few energy and it can be very fast. And if you're able to control, again, these nanostructures, the holes in this case, with atomic precision, you can have a very high selectivity. Okay. Now, the common challenge in these two examples is that you have to control the nanostructures at the nanoscale, again, at the below 5 nanometers, let's say. And you really cannot do that with the existing top-down approaches. And that's why we are here. And that's why we want to use the bottom-up techniques. So this slide would be just to convince you that you really need atomic precision. It's not a light sentence, that it's really necessary. Okay. Sorry. So the first one is related to the electronic properties, the one at the left. Okay. So these are calculations of the band gap that induce to graphene if you're able to make a ribbon, a very narrow ribbon of a different width. So this would be the width. And you have to follow the red dots here. Okay. These are the good calculations. So what you see is that the trend, as you decrease the width, is not monotonic, but is oscillating. And each of these dots is obtained by reducing the width only by one atom. You see that the jump from here to here of the gap, this is the band gap, is a factor of 4. So by changing one atom, by reducing the size of one atom, you change the band gap by a factor of 4. So you can imagine that it's very hard to make a device out of these ribbons if you don't have atomic precision, right? If we are thinking on the pores, for instance, the conditions are even harsher. This was these are some recent calculations of the ionic permeation. Okay, so they measure the current of these alkalis across these pores, and they apply some strain, very little strain. Okay, so now what we are changing is the diameter of these pores by a fraction of a carbon-carbon bond. And still we can increase the ionic current by a factor of 10. So you see how dramatic can these differences be. So if you are not able to control the pores with atomic precision, then I think that you are quite lost in this control of the ionic permeation. So I think that these are two examples of pores and also the material part of graphene, the ribbons, well, of the fact that you need atomic precision on that. So that's where we start. Okay, so this is the work between top-down and bottom-up. Okay, and I think these are easy examples of the two. You can build a charge with the top-down approach, as they did in Petra. And you can have very nice charges, but you have, of course, you limit in precision. You have also another limit, okay? That the material that you will have is the material that you had in the mountain. You cannot change the material. If you go to this other nice, very nice church, Sagrada Familia, I think that you know that, you see that you can add flexibility, you can add precision also, and that will depend on how good you are on building the bricks, okay, the building blocks. But this is not exactly the bottom-up approach that we are using. And I think that you will understand that by seeing or by knowing that this church was started to be built 140 years ago and is still not finished, okay? So you cannot build nanostructures with the bottom-up approach brick by brick. And that's why we need the self-assembly, okay? That's when we go to, so it's not only bottom-up, but it's bottom-up and self-assembly. We need to use nature to build the structures. And this is the real challenge. It's not the bottom up, because we are very good building blocks, or chemists are very good building the blocks, the initial building blocks. But we have to know how to put them together. Yeah? We have to control nature for that. So that's the real challenge, I would say. And that's where we are at. So this is the on-surface synthesis method. So what we use is The idea behind that is just to use surfaces in order to guide also diffusion of the molecules, but especially to guide reactions, specific reactions. This is not like CVD graphene. In CVD, you just add gas, small gases, hydrocarbon carbon gases on the surface, and you break them into atoms, okay, into carbon atoms, and then you build graphene. But here, what we have is some precursors, and we induce only particular reactions. We don't break the precursor, and that's important because these are our building blocks. Depending on which building blocks you will have different structures. So this is much more powerful than CVD. So this was demonstrated in 2010 by the group of Roman Fassel at EMPA in Zurich. And the reactions that, well, they followed are these ones here. So the idea is to use first halide monomers with halogens, okay? And to induce a particular reaction first, which is the so-called Ullmann reaction, where we first halogenate the precursor, you remove the halogens so that you have carbon radicals ready to react there, and the molecules then would couple, they would form a polymer. But these molecules here are, I mean, you have two anthracenes, they are three-dimensional molecules, and you still need to do a further reaction in order to have graphene-like structures. So you need to remove some hydrogens in order to planarize them. So that's a second reaction, the cyclodehydrogenation reaction that you can induce on the same surface by increasing the temperature. And by following these two steps and by changing the initial molecule, you can build quite a lot of carbon graphene nanoribbons. So this was really the onset of the on-surface synthesis of graphene nanostructures. And from there were really a lot of work, impressive work, that demonstrated that by thinking very well on the initial precursor, you can control basically everything: the width, the orientation of the edge of the structure, you can even functionalize. You can add new material, not as in Petra, okay? You can add new chemistry into the structures. You can now even add different bricks, okay? You can change the brick structure. So you can add to the nanographene some porphyrins, for instance. That was, I mean, this is quite recent work. But you see that in all these works, we are still quite limited on the length and the order, okay? So these two examples are just single structures, okay? You cannot just build standing structures out of that yet. And that's the state of art of the situation. You can really be very good at the small scale, very precise, but you cannot control the length of the order. This is the typical average length of nanoribbons that are reported. The maximum is 45 nanometers in average. So far, well, we have reported some other later. You could improve the order by, for instance, by nanostructuring your template, your catalytic template. You can add monatomic steps, and then you can force the growth in one direction. So this has been an important advance, because then you can align the nanostructures in millimeters, okay? You can have a single crystal made of these steps, and you can really have millimeters of a sample with all the ribbons aligned in one direction, but you cannot increase the length with this, because you are limiting everything to these terraces, diffusion included, okay? And you need the molecules to diffuse in order to incorporate into the structures. So this is a problem. So these templates are good for alignment, but they are not good for increasing the length. Or if you want to build some two-dimensional structures, well, then these are not the right templates. They are too hard. So we need smaller, softer templates, and that's exactly what we did in this work that you read, is to use a much softer template, which is on the very same surface of this material that they use for these stepped surfaces, which is the reconstruction of the gold surfaces. I didn't tell you that, but gold 111 is the surface where most of the reaction has been taken place. It's the one where the temperatures for the reactions are more separated and in the right scale. So that's why most of us are doing the reactions on gold. And the nice thing is that gold, the gold 111 surface itself is reconstructing into these nice patterns that you see, these zigzag patterns of in the order of 6 nanometers of periodicity. That's because the last atomic layer of gold is relaxed in a different way as the bulk. So the atomic distance that is optimum for this last layer is different, and therefore the stacking is not the same, okay? Some of the atoms like to stack in a given way, it's called HCP stacking, and other ones are stacked in a different way, we call them FCC, and in between you have some kind of domain walls. It's like a carpet that is roughened on top of the floor. And what it likes to do is this kind of zigzag structure. And each of these domains will be different for the molecules. So the molecules might prefer to absorb in one than the other one, and therefore we have a template to guide the diffusion, to guide reactions. They can be also different from the reactivity point of view. So this has been used to grow many different self-assembled structures. But if you want to make a straight one, this can be a problem, okay? So we want to build nanoribbons. This can be a problem because these are zigzag structures and our nanoribbons are not. And it happens that all the aromatic molecules prefer one of the domains, the FCC domains. So if you put molecules on this surface, they will try to fill these FCC domains and they will try to build structures here. But again, the nanoribbons are straight, so we have a problem here. I can demonstrate that by using this example of some molecules that we tested, okay? These molecules, these precursors, again, we have bromine atoms here. So these are our first, the ones involved in the first reaction, but all this structure is planar. That means that this planar structure will like to interact quite strongly with the surface because of the pi interactions of this aromatic backbone. And the interactions will be quite strong. And again, it will be preferred to be interacting with FCC domain than the HCP. And that means that when we grow the nanoribbons, following the same reactions as I told you before, the nanoribbons will try to be located on these rails, on these FCC rails, tracks of the zigzag herringbone reconstruction. So if you want to grow this kind of ordered structures, it's good, but you are again limited by the length here, because the periodicity of these zigzag structures is limited, okay? And it's of a few nanometers. I think it's like 10 nanometers or so, in the order of 10 nanometers. So what we need is not only less interacting or softer template, but we also need some less interacting molecules in order to have a different interaction with the substrate. And if you have that, then you can use a different template that this surface is offering you, and it's the kinks, okay? Here you have the kinks of these domain boundaries, and these are assumed with atomic resolution. And in the zoom, you see these defects. These are dislocation defects that are more reactive than the surface. And if you have molecules that they don't interact very strongly with the surface, so they don't differentiate between FCC and HCP, they can still differentiate or prefer to bond here. So they can use this template yet, even if they don't use the FCC, HCP zigzag template. And that's our trick. Because it happens that the network that these kinks are forming is linear. So if you manage to get molecules that can prefer or that are guided by these kinks, then you might be able to grow something that is linear and use this pattern to guide the self-assembly. And this is what we did with this other precursor, okay? So the key here with this precursor is that the interaction is through this phenyl, and apparently this phenyl is interacting weaker than the whole anthracene body. So, sorry, I have, okay, sorry, I had an interruption. So if you use this other precursor, the structures that you will be able to form when you polymerize and you remove the bromine are these ones. If you're able to planarize the system, it will be this one. So you will have this type of ribbon. But what we have to see now, what is important is to see if the precursors and these structures are following the FCC pattern or they are following the kinked pattern, okay? The kink network pattern. And this is these are STM images. I didn't tell you, but they are all STM images. I think that was quite clear. Of the first step, okay, when we polymerize the structures. Remember that these structures are three-dimensional. So that means that you can create you can create long polymers, but these polymers will interact between each other, again, with the pi-pi interaction of the rings. So these two structures will be interacting also laterally, and that means that they will form this kind of packed structures, okay? And as you see, all these packed structures are aligned on the surface. They are following one direction. And if we zoom, we see that this direction is following the zigzag of the reconstruction. So they are guided by the reconstruction. What we can also see is that they are all, all the packs, the bunches are started in one of the kinks, in one of these networks of these locations. So we can attribute to the kinks the guiding, the template. We can assume that they are the ones that are guiding the assembly of these polymers and the ones that they are ordering and aligning on the polymers. Now we have to see what happens when we are going to the second step, okay? When we want to planarize these structures. And when we planarize these structures, these are polymers again. So this reaction occurs at around 150, 200 degrees. When we planarize these structures, then we create nanoribbons. We know that from the atomic resolution images that you will see, or the high resolution images that I will show you later. But the important thing is that they are separated also, okay? And that's because now there is no more strong interaction between them, because they are not three-dimensional, they are planar. So all the pi-pi interaction is with the surface, which means again that the interaction is strong, which means that maybe more than being at the kinks, they prefer to be again at the FCC side. But now they cannot because they are too long. So they do what they can in order to be at the FCC side. And if we zoom in and if we see where the ribbons are located, we see that they are located at positions where they maximize the area with the FCC side. So it really seems, these positions are exactly the positions of these ribbons. It really seems that now they want to be at the FCC sites, but now it's too late for them to, and we already managed to align them before. So that's really a detailed balance of interactions. So with this, we are able to align ribbons. So that's an important thing. We are able to align ribbons at a certain level, of course. If we increase the coverage, we are able to grow ordered arrays of ribbons. So that's important if you want to control periodicity, for instance. But more importantly, maybe, or also, we are able to increase the length, because now we are guiding them, but we are still letting the molecules to diffuse in 2 dimensions, okay? So they can be very effective and they don't disturb each other very much. Sometimes you see that some of them crosses, like here, but usually they don't disturb each other and they can grow longer. And that's what we see here. If we make some statistics, we see that the average length that we have is at least 60, 70. I think that it's larger, but they are starting to be longer than the ones before. So that's an important requirement to control the orientation and the length in order to build devices. But that's also an important requirement if we want to build 2-dimensional structures. And that's the second step of our approach, okay? So far, there was no control assembly of these nanoribbons, covalent assembly of these nanoribbons, because the only way of aligning them also was by using these steps. Also because of the particular edge structures. If you covalently align 2 armature ribbons, you get just the same armature ribbon, but wider, okay? In our case, we had all the conditions in order to have an interesting structure. We had the alignment of the ribbon, which is all related to the particular interaction of the of the monomer and the surface. But also we have this interesting edge structure, okay? And this edge structure is allowing us to try a new step now, to try if the ribbons can also couple to each other by increasing the temperature, removing the hydrogens that we have here. And if we do that, we are very likely ending up on having this kind of structures that let us pores between the nanoribbons. So that means that we keep the integrity of the nanoribbon and the properties, and we add pores to the structure. And that's what we do if we increase the temperature. So now I start from STM images of the nanoribbons. We increase the temperature to 450, 550, and we start to see how they are adding or putting the coupling them together. We can do that with a more saturated surface, of course, and that's what we get. Okay, we have bunches of ribbons, spaghettis that are coupled to each other. Still, the size of these individual sheets or single crystals of this porous structure is in the order of 50 to 70 nanometer. Okay, in one direction is related to how long the ribbons were, that would be the maximum, and in the other direction on how well they can couple to each other, and on the orientation of each other. So this is a very important limit in these 2D covalent structures. We can zoom in and just to demonstrate, right, to show that we do have an interesting, that we do have a covalent coupling of these structures. If we take a CO molecule on the tip and we are working at 4 Kelvin, we can control this CO molecule and we can have much higher resolution, and we can really see the benzene, the graphene structure of these ribbons. So we can prove that this is covalent and that the structure is the one that we expect, and so on. So important parameters here is that we have a very, very high density of pores, okay? The highest you can have in one direction, because there's only one atom of carbon separating the pores here. Another important parameter maybe is that the pore size is below 1 nanometer, okay? So this is quite smaller than what we can get with top-down approaches. And all this is with a very low density of defects, okay? It's in the order of 1–2% of pores are defectus. So within these small nanocrystals, we can get perfect structures, but they are still small. Okay, so this is all the sequence. You go from a monomer to a polymer to a nanoribbon to nanoporous graphene, and you can stop wherever you want, depending on the material you want to have. This is a hierarchical reaction. So all the surface will, at the same time, have only one of these structures. This seems to be quite easy if you are lucky to get the right molecule and the right surface. Just to let you know that with the same molecule, just by changing the surface, you get completely different structures. So the surface is really critical, not only on getting the right length, but the right product, okay? And that's because, I can show you that with this example where we use silver, even different phases of silver or copper, and we never got nanoribbons, okay? The most we could get is just metal organic chains where, we could induce the halogenation, that's sure, it's easier because these are more reactive. But then, as they are more reactive also, they can incorporate silver atoms and they can form these metal organic chains. And you can have interesting chiral, non-chiral chains. You can planarize the units, but still you cannot, without forming the covalent structure in this direction. All these are interesting, but they are not nanoribbon. They are not covalent, they are metal organic. On copper, we couldn't even get order. So you planarize things and the two reactions are occurring at the same time and you cannot control them. Just to give you an example, that you have to choose both the right molecule and surface. Okay, I don't know how much time do I have. Peter? Is it okay?
Sure. So how far are you?
I have like 4 or 5 slides more.
Sounds great.
Okay. So I didn't prepare that. Okay, so I will give you now some insights in the properties of these materials. on the electronic properties of these materials. And we'll start with the theory. It is here because it's much more comprehensive than the experimental study. This is the band structure of the nanoribbons. This is the band structure calculated by DFT, by our colleagues in San Sebastian, of the nanoporous graphene. And these are, I mean, what we want to highlight here with different colors are different type of bands, okay? And what we represent here is the wave function of these bands at the gamma point, okay? So what we have is these three type of bands, very different. You can see that from the wave function. These ones, the yellow brownish ones, what we call longitudinal bands. These are existing in any kind of ribbon, and they are related to the pi bands that are dispersing along the ribbon. You see that they are delocalized all along the ribbon, but not this peripheral ring. We have these transversal bands. These are not dispersing along the ribbon. You see they are flat here. They are localized at the longest, widest stripes, okay? But they are not coupled to each other. And then we have these kind of pockets, much higher energy, that, I mean, the dispersion is quite small, so that means they are quite rather localized, and they are not dispersing, they are not coupled along, but they are in the vacuum. So these are not states that are directly related to the carbon atoms somehow, but more related to electronic states that are trapped between the vacuum potential and the potential of the carbon, the electronic structure of the carbon atoms. So they are vacuum states. So you see they are very different and they behave very differently as you make the nanoporous graphene. If you contact now the nanoporous graphene structure, these longitudinal ones will be very weakly affected because you have very small weights at the lateral bend centroids. So what we will see, I mean, the main effect that we saw at this time, is that the gap is slightly reduced, but still they are nearly one-dimensional. I think Matt will tell you much more details about what happens in the transversal direction with these states, because they have very nice detailed study of that. But let's say in the overall, they still behave in the one-dimensional, as a one-dimensional state, and the band gap is not much affected. The transversal ones, on the other hand, they still don't disperse in the transversal direction. They are not coupled, but now they can be coupled in the longitudinal, but now they can couple in the transversal direction. Because these ones are, I mean, the wave function is localized also in the connectors, okay? In this, so once they couple to each other, they can disperse in this direction. So we have states with opposite anisotropy here, or bands with opposite anisotropy. And then we have these pocket ones that when you create the pores, well, two pocket states will form this bonding and anti-bonding molecular states, okay? And you will have these kind of pore states that are in the vacuum. These are very high in energy. They don't disperse very much. So for making transport devices, transport-based devices, maybe it's not so important, but maybe they are very important for sensing because they are very sensitive to whatever it goes through or at the pore. So each one has its function. We could probe that experimentally. We can see the pore states at high energy. We can see how the energy is changing when we go from the pocket to the pore state. So this bonding, anti-bonding effect. We can see the band gap also. This is quite hard in these experiments because we have the gold, all the gold density of states. So people is always asking, but how do you know this is the valence band at the conduction band? Let me add only one more information. The DIDV, so the derivative of the current with respect to the voltage in STM, is proportional to the density of states, okay? So what we are probing is the density of state that is right below the tip apex. So with the same resolution as imaging. So that means that we can go to the pores and see what we have there, the density, or we can fix at one energy and map this DIDV. And that's what I show you here. So these are maps of the DIDV maps, so of the density of states at this energy where we identify the pore states. Okay, so this is the same as probing the square of the wave function, the probability. And with this, okay, just to summarize, what we get is experimentally a gap of 1 eV, which is what we would expect also from the theory. Yeah? The calculations are saying that in the freestanding membranes, it's 1.2. Then there is the effect of the gold and so on. But okay, basically we have a gap that is large enough, good to build devices. It's very difficult to explore the transversal states here because they are, as you see, they are combined with many longitudinal states, and that's really hard to identify. But that's the summarize of what we got. We have a new material, let's say, graphene-based material that now is semiconducting. It has a gap of 1 electron volt, but it's not just a semiconductor. It's a very anisotropic. So you have these orthogonal bands. Mats will tell you more about these states that they are not purely one-dimensional, but they talk to each other. And you have that in combination with some kind of pore states that maybe they are interested for sensing. And I would conclude, I mean, I was writing just very fast some conclusions that would be interesting maybe as a starting point for discussion, okay? That I was showing the beauty of the technique always. It's always nice to show the beauty and the power of a method to grow what you want, but then you have to really be sincere and humble and see which are the limits and where do you have to work at. And I think that these are the 3 limits, the main limitations I identified of this technique, which would be interesting to discuss. And one is still that it's limited on the scale and distribution. So we were improving that quite a lot, and that thanks to that we were able to extend the covalent synthesis to 2D, but still the sizes are small. Okay, so every time you approach somebody doing devices, it's like 50 nanometers. Well, where do you go with this? It's true that you can do a lot with a connected network of randomly distributed crystals, as in graphene. But if you really want to use the anisotropy, well, this is a problem. Introducing chemical heterogeneity is not straightforward, and I think I gave you one example, 1 year of a PhD. That's basically what it takes, or it can take. So we have to really work on the intelligent precursor designs, but also we have to learn quite a lot to predict what this will do on the surface, and that's what we are doing. This is on the infancy, I would say, this part. And very important to build devices. This technique or method only works on metallic surfaces so far, okay? And not in any metallic surfaces, as I show you. That means that if we want to make most of the devices that we want to make, they have to be on different substrates, many of them in insulating substrates, to gate, for instance. So we have to transfer. So we need really efficient transfer methods, or alternatively, ideally, we need to be able to grow on the insulator, or to be able to, well, manage to remove the metal in vacuum in a controlled way and place the nanomaterial in the insulator. And that's a challenge also. So that would be 3 important challenges in this field. And that's it.